All right, let's take a look at section 16.4, which covers Green's theorem. Start off by looking at a couple of our learning objectives. We want to define the orientation of a curve first, which means we'll revisit what we mean by a curve. And then we're going to get right into Green's theorem, which we'll see is just a bundle of joy. So starting with the orientation of a curve. First, recalling that a simple closed curve is one that starts and ends at the same point and does not intersect itself. Two examples of simple closed curves are given to the right, as well as the two orientations that we're going to talk about. So simple closed curve is the review part. The new part is going to be its orientation. So we're going to define two different directions, positive and negative. And we'll say that a simple closed curve is positive if its parameterization traverses the curve exactly once and in the counterclockwise direction. So here, the exactly once and the counterclockwise are the important bit. So just like the unit circle, where we measure positive angles to go in the counterclockwise direction, meaning that going backwards with a clockwise direction would end up being negative. So simple closed curve has a negative orientation if its parameterization traverses the curve exactly once, again, exactly once being important, in the clockwise direction. And if we go back and highlight the parts that are important, simple closed curve, again, starts and ends at the same point and doesn't intersect anywhere. But simple closed curves are going to be important for Green's theorem. So if we take a look at the statement of Green's theorem, here it is. We're going to assume that C, which is going to be our curve, will be some positively oriented piecewise smooth simple closed curve in a plane, and then D is going to be the region bounded by C. So if we take a look at this picture highlighted over on the right, we can get a visualization of what we're looking at. Some 2D region D with its boundary curve C. And then we'll define some vector function F, where it's got, we'll just label its components P and Q. And our vector function F must have continuous partial derivatives in an open region that contains D. Those are all of the important buildups into Green's theorem. So we need positively oriented, and we need a simple closed curve. Are going to be the things that we need to pay attention most to, as well as those continuous partial derivatives. Then we can apply Green's theorem, which what Green's theorem is going to do is relate a line integral around the curve C to a double integral over that 2D region D. So relating a line integral about the boundary of some region to the double integral over the region. And the statement itself of Green's theorem looks a bit confusing at first, but we're going to hopefully dissect that here in a minute. So if we again check over to the right, where we've got these couple of color codings listed, where I'll define F, that vector function, as having components P and Q, and color code them the way I've been color coding them, with purple for X and orange for Y. We'll see that the double integral in Green's theorem is the partial derivative of the Y component with respect to X minus the partial derivative of the X component with respect to Y. So those two pieces get mixed, and I think if we add a splash of color, it's a little easier to see what's happening there. And again, in a moment, we'll sort of figure out where those things come from, as well as why one piece of that ends up with a negative sign. Ultimately, that's going to be because of the orientations that we just defined. So we take one last look at just the statement of Green's theorem. We're going to be relating the line integral of a vector function to the double integral of a scalar function. So some sort of vector function, which probably means a parameterization along the boundary curve C, relating it to a scalar function that just happens to be the partial derivatives of that vector function f, but that goes all the way through that area that we defined as D. Before we get too deep into Green's theorem, though, we'll look at a couple of other ways that we can write it. First, I want to introduce a new notation for line integrals over closed curves, which is where we see this integral sign with a circle through the middle of it, highlighted with that green arrow pointing to that circle in the center. This particular notation is most common in physics. We don't see it quite as much in math textbooks, but in physics and in engineering, we like to use that circle through the integral sign to indicate that we're integrating over a closed curve. So that closed and positively oriented are going to be the important parts about putting that circle notation in the middle of our integral. Otherwise, it acts just like a regular line integral would. So again, we're using that circle to indicate that we're integrating over some closed curve. Or later on, it might be a closed surface if we're putting a circle through a double integral. But again, circle through the piece means that whatever curve we're integrating on is closed, as opposed to just integrating some line that has a beginning and an end. We'll also give a different notation for C. So if we just want to define our region D, again, is that area, oftentimes we'll use delta D to represent its boundary curve instead of C. So if we look at the restatement of Green's theorem, we have delta D and D instead of C and D. Also, if we take a look at, we've got P appears on the right and Q appears on the left, even though P is the X coordinate or the X component and Q is the Y component of that vector field F. And the partial derivatives that we're taking do not match the component position. So they alternate. One last thing to mention over on the right is that if we have some parameterization R that's going to be parameterizing that boundary curve C or delta D, depending on which notation we want to use. So we have some parameterization R of T where the components are X of T and Y of T, meaning just X and Y, are functions of some parameter T. Then we can have F dot dr look like P dx plus Q dy, where dx and dy are probably going to represent some function being multiplied by dt. So x is a function, we'll take the derivative of x with respect to t and then multiply it by dt in there so that we can integrate this thing with respect to a parameter. And we'll sort of lovingly call this the scalar form of that line integral that we'd established earlier. So we'll kind of go back and forth between the two different forms that we use, either f dot dr or p dx plus q dy, but they both represent the same line integral along that boundary curve C. All right. Now that we've introduced a whole bunch of notation, we're going to try to look at where the heck Green's theorem comes from. So, the proof of Green's theorem is notoriously quite difficult. So we're not going to get at all into the nitty-gritty of it here. Although I do want to at least look at pieces of it in order to just kind of give us some idea of where Green's theorem comes from and what it's actually doing. So this isn't going to be a rigorous proof of Green's theorem by any means. I just want to look at a couple of pieces and kind of get an idea of how to piece together this double integral to get into the line integral and see how they relate, and then hopefully relate this back to a Calc 1 topic to give us a little bit of a better understanding. So I've just taken that double integral piece where we're taking the double integral of q partial x minus p partial y times dA, and we're going to split that up into two separate integrals, one that's integrating partial q and one that's integrating partial p. So if we look at dA, and in terms of x and y, dA is either dx dy or dy dx, depending on the order that we want. And I'm going to write it in a different order for each of the two integral pieces that I'm breaking it up into. Since if I have the q partial x, I want to integrate that thing first with respect to x, so I can just get this thing back to q and y. So that in the end, my goal is to have just one color in each of these two integrals. So just yellow for the y part and purple for the x part. And since this isn't going to be a complete or rigorous proof of Green's theorem, just I want to highlight a few pieces. I'm just going to look at expanding that integral on the right. And we'll say that the integral on the left is going to mirror this one to some degree, but hopefully just looking at this one should give us enough of an idea of what's happening here. So let's bring that down to the next line, where we'll bring in a figure of just some nice looking shape, which again, we're going to take some of the rigor out of the proof, so that we're not going to do the whole thing, and just say that we happen to have a nice type 1 region that we want to integrate over, meaning that the double integral can be quite nice to do dy and then dx. So the double integrals represent the blue part that I've highlighted up above, and we've got some curve C, but that's split into 4 different pieces, and say that we're going to take that double integral of p partial y and kind of split it up and see what it is that we're actually doing. Well, since I elected to do y first, I can now start finding some bounds for both y and for x. The bounds on y are going to be the top function and the bottom function. Here they're labeled g1 and g2. g1 on the bottom, g2 on the top. And then x can just integrate from a to b, since this is a nice, simple type 1 region. Doing so means that we can just take that integral there in the middle, and using the fundamental theorem of calculus from all the way back in Calc 1, I can just integrate p with respect to y, and then plug in g2 at the top, plug in g1 at the bottom, take the difference, and then I still have another integral that I could do in terms of x. We're not going to quite take that step because I just want to be able to relate a double integral to a single integral, but this is our first step. It's just rewriting these couple of pieces. Then if we break that piece again into 2 separate integrals, that negative sign will distribute so that along the g1 piece I end up with a positive integral, while the top piece where I've got g2 is still negative. And now we should relate the idea of orientation from those simple closed curves that we looked at a moment ago. Where if I'm looking at integrating along G2 from A to B, the curve C3, as long as I'm going in a positive orientation, which if we look over at figure 3, we can see that the arrows are all going counterclockwise. So this thing is positive, but I have forward directions labeled in green, while backward directions are going to be labeled in red, because in order to do that integral along C3, I have to go backwards. I'm moving left along that curve C3. So along the function where y is equal to G2, I want to move from left to right. Meaning that instead of integrating from A to B along G2, I would prefer to integrate from B to A, meaning I should switch the sign of that integral. So it's going to change from negative to positive. And it's this particular orientation that will explain why that p partial y is negative in the statement of Green's theorem. If we were to look briefly at what would happen if we had done q instead of p, for doing q, we'd want a type 2 region, which means we're going to split it up into a right function and a left function for x. And we can see that in the case of a type 2 region, our rightmost function is moving in the forward direction, whereas our bottom function is moving in the backward direction. Which is why the q piece is positive, but p is negative, because again, it all comes down to that orientation. If we're looking right to left, our right side is going forward, but if we're looking top to bottom, our top side is going backward. That's probably a bit deeper than we really wanted to get. The part that I want to look at here is that I have two integrals, just single integrals from like back in Calc 1, that represent a line integral moving along the curve C3 and along the curve of C1. And if I wanted to do my entire closed curve, I would just need to add in the line integral over, or the integral across the line C2 and C4 to this piece. But since we, just cherry picked ourselves a nice type 1 region, integrating along C2 or along C4 with respect to x, both of those are vertical lines, which means that dx is 0. So the integral along C2 or C4 is just going to be 0, because again, there's no change in x, so there's no area that would come up there. So yeah, again, integrating along a vertical line means that I would get 0 if I do a definite integral there. So C4 and C2, which are added in there at the end, both are going to be 0. But since those line integrals are 0, adding up all four pieces, an integral across C1, C2, C3, C4, that gets me the entire line integral of P across the closed curve C. So all together, what we were trying to relate here, our final result is going to be the line integral of P along the curve C with respect to x. But we started with that double integral of P partial y times dA over the 2D area D. So I wanted to demonstrate here that we were able to relate one part of that double integral to one part of that scalar form of the line integral that we wanted to use. And again, I only really wanted to highlight the one direction. It's pretty much the same if we did Q. We would just want to look at a type 2 region for simplicity's sake instead of a type 1. Meaning that, again, this is by no means a rigorous proof of Green's theorem. We're just trying to get a bit of an idea of where it comes from. You can check the textbook for a slightly more in-depth explanation than is presented here, but you'll see that it gets a bit more into the weeds than I did, which is impressive because we're pretty far in at this point. But the takeaway here is that we were able to traverse along each of C1, 2, 3, and 4 to get the total line integral of P dx, even though we started with the double integral over D. So if we bring this thing back around, and if you'll just let me kind of wave my hands and say that I promise if you do Q, you're going to get the same thing. We'll say that that double integral over the region D of the two opposite partial derivatives of Q and P, which were the components of our vector function F, we end up getting a line integral of Q dy plus a line integral of P dx. And if we just recombine from that scalar form back out into the vector form, we end up with the simpler statement of the line integral of f dot dr. Again, assuming that r is that nice parameterization where the x component is x of t and the y component is y of t. Yay, Green's theorem. Isn't it so much fun? Okay, let's see if we can actually come up with a bit of a takeaway that is less technical than everything that we just dove into there. That was admittedly quite a lot. So we used the fundamental theorem of calculus when we were setting up that integral to get from the double integral to the line integral. And that is kind of how we want to think about Green's theorem. It's not exactly analogous, but it's about as close as we can get in the double integral world, having a fundamental theorem of calculus for double integrals. So when we see Green's theorem, we want to think of it like it were the fundamental theorem of calculus. So if we just recall what that fundamental theorem is, it says that if I integrate the derivative of f from a to b, then that's the same as evaluating the original function f at its two endpoints, b and a, and taking the difference. Fundamental theorem of calculus said that that's what we wanted to do. And we want to relate that idea to Green's theorem. So if you sort of follow the green highlighted portions of those two theorems, hopefully we can start to see where that analogy comes in, right? So I want to be, if I'm looking at the green portions of each, I want to be integrating a derivative of some kind to then looking at the evaluation of that function at the endpoints. So again, fundamental theorem of calculus, integrate a linear function or integrate the derivative of a linear function, and I can just plug in the endpoints. Green's theorem is going to say that if I want to take the double integral of some partial derivatives of a vector function f over some area d, that is the same as taking the line integral of that vector function, but with values plugged in along the boundary. So think of, if we go back to the fundamental theorem of calculus, just the Calc 1 version, think of A and B as the boundary of whatever one-dimensional region that I wanted to integrate over. Green's theorem says that, well, we don't have just two endpoints anymore because we're in two space. So instead of being able to just have a simple evaluation at the beginning and the end, I want to relate the double integral over the interior area to the line integral of the boundary, where the boundary can kind of be analogous to the endpoints from an interval back in Calc 1. And we end up reducing our overall integral count by 1 when we use either the fundamental theorem or Green's theorem. Because Green's theorem says we go from a double integral to a single line integral, whereas the fundamental theorem of calculus says that we go from the integral of a derivative to just that function, but with its endpoints plugged in. And same thing here, we have some partial derivatives that are on the inside of the double integral to just the original function f being on the inside of that single line integral. Oh yeah, so that's Green's theorem. Yee-ha. Let's see what happens if we try an example with it. So we want to find the work done by some function f. Think of this as some sort of force field we've got going on here. Or we're going to go once clockwise around the curve given by the picture to the right. So one of the things that'll be helpful to know is the formula for work. And as if we have some non-constant force f, then work ends up being the integral of f dot dr, where dr will describe the path taken and f is that variable force. If you've seen some introductory level physics, you might be familiar with work as being the product of force and distance, which works out great if we have some constant force. But if our force is not constant, as is the case here, then we need to update that definition of work so that it includes a little bit of calculus. So work will be defined again as the integral of f dot dr, which happens to look quite a bit like a line integral, which is what we've been looking at. And we're also going to be pushing this thing along some closed curve. And as we can see, it's also a nice simple curve, which means we ought to be able to apply Green's theorem here as well. So if we take a look at this curve and start traversing it counterclockwise exactly once, pick somewhere to start. My favorite spot would probably be just along the x-axis and furthest to the right, and then just start moving counterclockwise. So we'll go up this way, and we'll get our first curve, C1, then move along this horizontal line, get our second curve, C2, then across this small circle, which we're going to be moving It almost looks like we're going clockwise now, but overall this is going to be a counterclockwise orientation as long as we start from the beginning. So that's C3, and then close it off to get C4 also along that horizontal line. Where if we just throw some arrows in to remind us which direction we've been going along each of these lines, that's going to be our single once around in a clockwise direction. So I've got my curve C, which we had to break up into 4 pieces, C1 through C4. And I could get equations for each one of these lines, C1, C2, C3, and C4. Let's maybe slide that over a little bit so that they all line up. Across the curve C1, we have the top half of a circle that's radius 3. So that should be y is equal to the square root of 9 minus x squared. We only want the positive part there. C2 is just a straight line, so that's nice and easy. It's the line y equals 0. C3, now we're going along the top half of a circle of radius 1. So we'd have y is equal to, again, positive square root of 1 minus x squared. No need for a plus or minus here because I only want the top half. And then C4, again, I'm along that horizontal line of y equals 0. So I can describe each one of those curves. And then if I really, really wanted to, I could take a line integral along each piece. It'd be 4 separate integrals, but I could come up with the work done. And I'm here to tell you that that is likely a giant pain. So let's not do that. And instead, apply Green's theorem. Hey, what a surprise. It's the section on Green's theorem, and we're actually going to use it. So let's get cracking on this thing. So instead of doing 4 line integrals, I want to do a double integral over some partial derivatives, where I am going to want, I'm going to start with q, but I want partial x, and then I'm going to subtract p, being the x component, but I want the partial y this time. So p partial y, and then all of that is in terms of dA, and this is over some region D, where D is going to be a piece that's that 2D region that's on the inside of the curve that we just sketched. So we were looking at going over some curve C, but now we want that interior region D. Looks like maybe we could shade that in. Right? Ooh, crap. So if we just shade in that region D, it's the blue part, it's the interior region. So we'll end up wanting to describe that using dA, but for now, we ought to be able to just come up with q partial x minus p partial y. So don't forget that p is the x component, while q is the y component. So we're going to be looking at the double integral over our region D of q partial x, which is going to be 2 minus 0. So 2 minus p partial y. And if we do that, we're going to get 0 minus 2. So 2 minus 2 dA, or 2 minus negative 2 dA. Since we're subtracting a negative, that should really come out to 4 times the double integral of dA. And here's where we'll actually need to take some integral. But since we're working with mostly curved surfaces, like we've got 2 circles in that region that we're looking to integrate over, looks like it's going to be way nicer if we convert this thing to polar coordinates and then run some integral there. So if we make that swap real fast, this will be the double integral of r dr d theta, dr d theta. Well, let's actually color code these in as well. Seems like we were using red and green. Where, let's maybe fix up those integral signs so that they're going to look a little bit nicer for us. R is going to need to integrate from 1 out to 3. Since we don't want to include the inner part of the circle that goes from 0 to 1, we just want the part between 1 and 3. And then theta, well, we're only doing the first 2 quadrants because we just wanted the top half of each of those circles, which means theta should only go from 0 to pi instead of the usual, oftentimes we'll do 0 to 2 pi. And this thing is a nice separable integral, so that can be 4 times the theta integral, which is just going to come out to pi, times the r integral. We'll have r squared over 2, where we're playing in 3 and 1. So we've got 9 over 2 minus 1 over 2 is 8 over 2. Multiply that all together, and I believe we end up with 16 pi. So again, applying Green's theorem, this particular time it was way nicer to do the double integral than it would have been to do 4 separate line integrals. So we used Green's theorem to say, okay, I can see I've got this line integral, but I'd much rather just do a quick double integral, which happened to work out really nice. Because it was basically just integrating the area of some simple region. At least it was simple if we were in polar coordinates. So let's try that out, but with one more example. So this time evaluate the line integral over the closed curve C. So don't forget that little circle in the integral means that we've got a closed curve C, where we've got something dx plus something else dy, where C is the boundary of the square with vertices 0, 1, 1, 0, 0, -1, and -1, 0, or just the sketch that's listed below. So it's basically a square, but it's rotated 45 degrees. So if we look at the line integral provided, we should see that it matches that scalar form of Green's theorem, where we've already multiplied out f times dr, and so now we've got p dx plus q dy, as long as we continue labeling f in that same nice way. So our vector field f, or our vector equation f, is p for the x component and q for the y component, or purple for x and yellow for y, to kind of help use some color to keep track of what's going on. And once again, we could break this thing down into, well, what could we break it down into? We could break it down into four different lines, do a line integral along each one. So if we say started at that same point, start along the x-axis and move in a counterclockwise direction, we'd be going this way. So we'll call it C1, C2, C3, C4. Notice it's not particularly relevant which one we call C1 or C2, or where we want to start labeling 1, 2, 3, 4. It's just always helpful. If wherever we start, we continue moving counterclockwise as we name each consecutive piece of C. And like I said, my favorite is to just start along the x-axis because that's where the unit circle starts. Just makes the most sense in my brain. So I started with C1 right there. And we could come up with equations for each one of those lines once again. So C1, C2, C3, and C4. And it looks like for C1, we'd have the equation y equals 1 minus x. For C2, that must be the equation y equals Is that x minus 1? I think. Oh, no, never mind. That's not x minus 1. That's x plus 1. There we go. For C3, we've got a negative slope once again. So this is going to be, looks like -1 minus x. And for C4, this time it's x minus 1. There we go. So we could parameterize each of those 4 pieces of C and do 4 separate integrals, add them all up to get the total line integral over the closed curve C. But that seems like a pain, and I'd rather not. So instead, we'll use Green's theorem once again. Just take the partials of those 2 components of f, so the partial of p and the partial of q, but we're going to want q partial x and p partial y, and say that that line integral over the closed curve C is equal to the double integral over the region D, where D is that blue square that's been rotated 45 degrees. And again, we want q partial x minus p partial y. And then multiply that whole thing by dA. So if we actually look at getting those partial derivatives, what is it that we're going to have? Integrating over the region D, q partial x comes out to just 5 plus 0 minus, we're going to want to do x partial y, which will be 0 plus 2. So in the end, I've got 5 minus 2 dA, which is 3 times just the integral of dA over my region D. So really, it's just 3 times the area of that region, which, if we use either the Pythagorean theorem or the square diagonal theorem, if you're familiar with that one, the diagonal of that square is 2, which means that each side of that square is going to have a length of the square root of 2, or Pythagorean theorem, if we just kind of break down one of those triangles, say the one that's in the first quadrant, both legs are 1, so the hypotenuse is the square root of 2. All that to say that the area of that thing should be the square root of 2 squared. It should be the area of our region D, since the area of a square is just the length of one side squared. And yeah, squares. How do they work? Miracles. Anyway, enough of my rambling. That looks like 3 times 2. So overall, that line integral has a value of 6. And we used Green's theorem to get there. Again, we could do each one of those line integrals. We can parameterize both q and p. I've got everything listed out as y in terms of x, so I can replace all of my y's with those functions of x. And then I have 4 single variable integrals. Most of the time, it looks like we'll be integrating from either 0 to 1 or -1 to 0. Add them all up, and we should hopefully see that we get 6. But if you did all that work, I think you might agree that using Green's theorem to just do the double integral is significantly nicer. So we're probably going to go with that. And that wraps up Green's theorem.